Hello, my name is Aaron Crawford.
And my name is Alexander Cockerham. We represent the University of Central Florida, team 1146. Our coach is Dr. Zhisheng Shuai.
This modeling competition, we chose to do problem A, and this is to find the decay of oil agglomerates from the Deepwater Horizon accident. The overview of this project, the Deepwater Horizon spill has caused oil to wash up upon many shores. These crude oil compounds have formed SOAs, otherwise called sediment oil agglomerates. We will be modeling these SOAs based on research gathered in the paper, Decomposition of Sediment Oil Agglomerates in a Gulf of Mexico Sandy Beach. Developing the basic model. The flow rate of the sediment was thought to be an important factor. The two main forces affecting this were the tidal pumping force as well as the force produced by wind. Through Darcy's law for fluid flow through permeable material, we found that the force of wind did not present a necessarily volumetric flow rate past a depth of 10 centimeters. This led us to believe that the flow rate is determined mostly by the tidal pumping force, as put forward by the paper. The importance of the flow rate in this model is due to the exchange of nutrients that help in biodegradation by bacteria, as well as the exchange of compounds which have been broken down into gases. Though we would like to have created a model based on this flow rate, it proved to be too complicated, and we instead used a steady state model.
I'm going to start off with the assumptions of the basic model. We're assuming that the growth period of the microbes has already been accounted for and that any microbes present on sand oil agglomerates is consistent throughout the course of the experiment. We're also modeling the mass on a basis of exponential decay, where rate constant is average decay of constant for all alkenes for the basic model. The decay rate is assumed to be tied to moisture, and we model moisture later on as a function of depth and porosity. But in the first model, we assume this to be constant given depth and porosity. Temperature over the course of all of our models is assumed to be steady state. And as mentioned earlier, we're assuming that any sort of flow of moisture is constant such that moisture is not changing over time. I'm going to go over the first model that we chose to use. It's based on exponential decay derived from the first order chemical differential rate law equation. This is an example of our first model showing the mass over time for an average standardized sand oil agglomerate used in the paper. You can see we used the rate constant of 0.0022, which was derived from data provided by the publishers of the paper, and it is average for all alkanes.
For developing the next model, we decided to set up a differential equation with mass tied to the decay rate. This is assuming that the microbes would decrease in size and have a decay rate relative to the mass. As you can see, we were left with an exponential function based on a function of depth and porosity as the exponent plus a constant. Comparing this model with the model from the paper, we note several key differences. The first is that their model assumes a decay rate irrelevant of depth, while our second model does in fact count for depth when finding the decay rate. Our model also starts with a constant of 4.8, representing the 4.8 grams of the initial oil substance. Their model is not correct for time zero and is based on a percentage originally, which we turned into a mass function to be similar to ours. Interpolating data from their graph, we were able to find a function of decay rate due to depth of the SOA in centimeters. We did this as a piecewise function in order to have both halves of the peak at 28 centimeters in depth be related accurately to the decay rate. The basic model with the decay rate based solely on depth. This model, for the most part, is comparable with the figures suggested by the researchers, though I believe that at the decay rate of 20, the constant is too high and leads to 90% decrease in total carbon content over 6 years, as compared to 32 years for a depth of 10 centimeters. It could be possible that the discrepancies were found due to measurement issues, as denoted by the error bars in the previous graph. This model focuses on carbon content as opposed to the amount of harmful material left, which could be another issue. A more advanced model, which we have denoted as Model 3, was also created. This model focuses on the decay of alkanes and PAHs, the two harmful chemicals that make up the majority of this oil substance. This model was created by adding together the rate of change of both the alkane mass and the rate of change of the PAH mass. The two equations were formed similarly to the first equation and added together, with the constants being the relative mass of both the alkanes and the PAHs, denoted by C1 and C2. These decay rates for Model 3 were found based on graphs in the research paper. The top one is the decay rate of alkanes, and the bottom one is the decay rate for the PAHs. We will now be looking into when oil reaches 10% of its original mass, based on Model 3. This will be done using the decay rates for alkanes and PAHs. Through graphing the function, it was found that approximately 1,414 days were required to reach 90% of the original mass of PAHs and alkanes. After about 5,900 days, there were virtually no PAHs or alkanes left.
In order to improve our model, we decided to parameterize depth and porosity into the rate constant for the chemical decay of carbon compounds and hydrocarbons. To account for depth, we fitted a logistic growth function to the data that were present for the decay rate of alkanes over time. We noted that for all given carbon chain lengths of alkanes, as well as PAHs, the decay rate at 40 centimeters was roughly 3 times the decay rate at 10 centimeters, 10 centimeters being the cutoff point at which depth is deep enough for moisture to be constant and aerobic decomposition from bacteria to be the main contributing factor to oil decomposition. X was parameterized for depth from the logistical function, and the rate constant is defined here above as x times y times 0.008734, which was done by standardizing the porosity to be 0.49 and the depth to be 40 centimeters. The new model accounts for porosity and depth as parameters, and we can test with multiple different porosities and depths what the decay rate is for the carbon and how much mass would be left after a given amount of time. Here we have held porosity standard to 0.49, which is the porosity of sand present in the beach from the paper. And we have varied the depth from 10 centimeters to 60 centimeters with this model. Starting at a depth of 10 centimeters, the decay rate is seen to be considerably slower than lower depths. As depths approach 50, 60, and onwards in terms of centimeters, the decay rate standardizes and stabilizes. So any oil buried past 60 centimeters or so will not statistically vary significantly from oil buried at lower depths than this. We've assumed the logistical growth model for the depth to approach normalized value of 1, meaning maximum moisture in terms of depth. This means that at lower depths, the moisture as a function of depth is lower, meaning that the decay rate is lower and it increases as depth gets deeper. Here, we have standardized depth to be 10 centimeters, and we've shown the difference in porosity for the model. The minimum porosity that allows for permeability and moisture for the sand is 30% porosity, which is the critical porosity for sand. Here, we have held the depth constant and used different porosities for sand. It should be noted that as the porosity approaches 100%, obviously it won't really hold true and the model won't be stable and valid at those values. And it should also be noted that at very low porosities, the mass over time decreases very slowly relative to greater porosities. In the paper that we have referenced, porosity of 0.49 was used, and it approaches roughly higher porosities as they start to asymptotically approach a given value denoted around the porosity 0.7. Here we've used model 4 in order to determine the point at time at which 10% of oil mass will be remaining. We did this using the same methods as before, but using the new updated model. We've set porosity to be 0.49 in line with the results of the paper, and the depth to be 40 centimeters in line with the maximum depth at which carbon decomposition was greatest in the paper. Here, the carbon and oil is 90% decayed after 2020 days. We wanted to look at the effects of removing sediment layers in order to see the effects of oil decomposition when the top layers of sand are removed. As stated earlier, in the top layers of sand, aerobic bacterial decomposition of oil is not the primary contributing factor to the oil decomposition, and the rate is much slower. As such, below 10 centimeters, the aerobic respiration and decomposition of oil is the main contributing factor and has a greater contribution and greater decay rate. Since removing sand will cause aerobic decomposition of SOAs to no longer be the major cause of decomposition, it'll be slower and driven largely by temperature and photochemical decomposition. Effectively, removing 10 centimeters of sand would push the decay rate of oil buried 20 centimeters below to 10 centimeters, meaning that the decay rate will shift to be effectively the same as if it was buried 10 centimeters below. In conclusion, the fourth version of our model shows the mass of sand oil agglomerate over time, accounting for porosity and depth as parameters that affect the rate constant of oil decomposition. This is following the steady state approximation that temperature and moisture are constant over time and over the course of the year. We assume this to be valid in line with the time scale at which we're looking at the oil decomposition.
The reason for having 4 models was both to build upon previous models, as well as to play the strengths of each model. Even from the first model, we got an idea of the relative exponential decay rate that this oil will face due to microbial decay. Going towards the 4th model, we decided to add in the porosity and the depth as a function to find the decay rate. We appreciate you listening to our explanation of our models. We both have learned a lot and have grown in our knowledge of differential equations.